Good afternoon. I come from a culture where siesta is very important. So I know the risk of this time for a presentation. I'll try to keep you awake. The other thing is, I was thinking when I was invited, and first of all, thanks to the organizers for inviting me to this Congress, I thought, what can I say about climate change in an audience where climate change is probably not a priority subject? And I'll tell you what I tried to do. Or I will be happy if you guys leave this room thinking about climate change in a different way as you have been thinking so far. If you haven't thinking at all, I hope that you start thinking a little bit about it. And just to be sure that we know what we're talking about, that cartoon is describing the greenhouse effect. And basically the sun sends radiation, some of that radiation is absorbed in the planet, is re-emitted as infrared, as heat, and part of that heat is reflected by gases that have this greenhouse effect ability. This is a natural greenhouse effect. If we didn't have this natural effect, today it would be 10 or 15 degrees colder than what it is. What has been happening is that the human activities have been resulting in emissions of these greenhouse gases in such a way that it's similar to having a greenhouse with a thicker glass. So now you get more heat being trapped. And the importance of that increased heat being trapped is that it intensifies the hydrological cycle. So it is important that the temperature gradually increases. I think for us, for most societies, it's more important that the hydrological cycle is intensified. And then that results, or that can result in having more variable climate, more droughts, more floods, etc. And we'll talk about that in a little while. As you probably know, there is a big debate about how much of these changes in climate can be attributed to human activity and how much is just natural. To be honest, at least in the institute where we work, we don't care. We really don't care how much this is attributable to human activities. What we know for sure is that human activities affect the phenomenon, and therefore something has to be done. That's the premise. I really think it's a waste of energy to try to quantify how much is due to human activities. We know that human activities have something to do with it. Now, if you look at the global emissions of these greenhouse gases, you see this very complicated flow chart. But basically, what it's saying is that more than 60% of these greenhouse gases are coming from the energy sector, and 18% from deforestation and 14% from agriculture. So this is important to keep in mind. It's important to keep in mind how responsible is agriculture in the global picture. Now, there's one thing that is very important about the agricultural sector. Although the total amounts of this CO2 equivalents may look small, from agriculture come two emissions of two gases that are the methane and the nitrogen oxides, that they have a greater heating power than the CO2, than the carbon dioxide. Methane has 25 times the power of CO2, and the nitrogen oxides 300 times. So again, something has to be done about this in the agricultural sector. And basically, there's two things that can be done with respect to climate change. One is go to the causes. In the climate change jargon, this is called mitigation, and basically it's reducing net emissions. What is that? It's either reduce emissions or remove gases from the atmosphere, which is called sequestration. I'm not going to discuss any of this. You can imagine what are the most important actions that are needed in this area, in mitigating climate change. Renewable energy, efficient transportation, reduce deforestation, reduce these methane and nitrogen oxide emissions. And from the removal of greenhouse gases, there is the carbon sequestration in soils, that is, trap CO2 that is now in the atmosphere in forms that remain in the soil, or increase activities such as planting trees. I'm not going to talk a lot about mitigation. I'm just going to have two comments. One is about carbon footprints. You probably heard a lot about that. And that basically means how much CO2 equivalent, how many kilos of CO2 equivalent are emitted to produce, say, 1 kilo of meat or 1 kilo of milk. The reason why this is important is because it wouldn't be a surprise if these start becoming non-tariff barriers for countries that are in the international markets. And therefore, there is a clear need, not only scientific need, but commercial, economical need to start measuring the carbon footprints. And measuring, it's not easy, and they have to be measured right, in a way that is undebatable. The other comment is there are some countries in this region, at least, that there is a very large potential to work on mitigation, reduce net emissions by sequestering carbon, by just working on land use changes. I'm not going to, as I said, I'm not going to discuss this a lot. I'm just going to say a couple of things about measuring carbon footprints. One thing is that it can be measured. These are results from a group in the University of Uruguay by a researcher that now works for INEA. And basically what she did is measure how much of this carbon footprint is produced in different stages of the milk production. One good news is that increasing productivity results in decreased footprint. For example, you get less CO2 per kilo of milk when you get more milk production per hectare. That is good. And it's also true that you also get less emissions of CO2 per kilo of milk when you increase the productivity per cow. This is all I'm going to say about this, and for those of you who are interested in this area, this afternoon at 3:30, there's going to be a panel discussing these issues. So mitigation, I hope you understand from this part of the presentation that the key issue here is mitigation, is reducing net emissions. But the truth is that even if we stop the world today, stopped all emissions today, the inertia of the past and present greenhouse gas emissions will result in effects on climate that will last at least 40 or 50 years. Therefore, this is the second action in climate change. We need to adapt. We need to adapt to a changing climate. Now, science is supposed to inform decisions, to inform public policy. And therefore, when the scientific community working in climate change discusses this issue of improving adaptation to climate change, the first question that we get asked is, what do we need to adapt to? What will the future climate look like? So we need to develop future climate scenarios. And what are the best tools that we have for that? The climate models. Climate models are very complicated computer-based programs that divide the world into little grids, like you see in that diagram. And then for each grid, they take several layers up into the atmosphere and several layers down into the ocean. And then just following laws of thermodynamics, heat exchanges, etc., they simulate the circulation of the atmosphere. These models are the same type of models that I use for the weather forecast, to know if tomorrow it's going to rain or not. Except that in this case, the climate community, the scientific community, modified these models to change the chemical composition of the atmosphere here in the layers of the atmosphere to simulate what would happen if you increase greenhouse gas concentration. Now, billions of dollars are being spent to improve these models. And one example in which to show how these models have been improving is they're becoming more and more, the resolution is becoming higher and higher. So if you look at the earlier models, the ones on the top, that's Europe. You couldn't see the Alps. Here they couldn't see the Andes. In the most recent models, now you have a lot more definition, which is good, simulate the topography much better. And also the amount of layers up into the atmosphere and down into the ocean have been increasing. So as a result, the models are getting better and better. Now, like any other issue in scientific knowledge, this is work in progress. And so just to show that, this graph is showing the best available models. There's about 40 or 50 of those models included in IPCC reports. The last report will come up this year. And what that is showing is the evolution of rainfall during the 20th century. So this is not projecting future. This is how the models see the past. Precipitation in a window that includes Southeast South America. So South Brazil, Uruguay, a piece of Argentina, a little piece of Paraguay. And basically what the models are seeing is that during the 20th century, precipitation in September to February increased, right? So the envelope includes the 50 best climate models. And that thicker line is a mean of all the models. This is how the models see reality. Now, look what happened in reality. Completely different. Precipitation in this region increased a lot. And none of the models has been able to see that. I chose this area for a reason. The reason is that the models don't work very well here for that. But what it really means is that, like as I said, in any scientific area, this is work in progress. Models are getting better, but there's still a lot to learn. So when we try to use these models to imagine the climate of the future, we have that first limitation. We don't know everything about climate. But then there is another limitation, which I think it can be even worse. In order to use these models to imagine the climate of the future, we have to imagine how the emissions will be in the next 40, 50, 70 years. We have to imagine what energy sources people are going to be using. We have to imagine how much deforestation. We have to imagine the world 80 years from now. Who dares saying what the world will look like in 80 years? Very difficult. So, what did the climate community do? They said, well, let's think of different possibilities. Let's think of scenarios that are very optimistic, lots of renewable energy, lots of technology transfer between the countries. And let's think of very pessimistic scenarios. Business as usual. Fossil fuels will still be the main energy source, etc. And so, with all those, the range of possible scenarios, then they say, well, if we are optimistic about the future, the emissions of greenhouse gases will be low. If we are less optimistic, more pessimistic, then the emissions of greenhouse gases will be high. And then they connect these scenarios with the climate models to see what the climate may look like in the future. And you get this type of results. So this graph is showing, in gray, observed temperature of the whole planet. This is not a country, it's not a region, it's not a continent, it's a whole planet. Up to the year 2000, and then in red, light blue, blue, orange, is what the models are saying that will happen with the global temperature, the temperature of the whole planet in the next 80 years. And basically what the models are saying is that by the end of the 21st century, the temperature of the whole planet will be very similar to what we have now, up to an increase in 7 degrees, which is similar to telling you by the end of the century, 1 kilo of beef in the international market, you can expect that the price could be between $3 and $45. So try to make a projection, try to do estimation of margins producing meat. There is a mean value. Mean value between 3 and 45 is, I don't know, 20. But the huge range. Why? Because it's uncertain. There's a lot of uncertainty. This is for the planetary temperature. For rainfall, it's much worse. For rainfall, this graph shows when you see some colors, that means that 2/3 of the models agree in the sign. If it is bluish, 2/3 of the models says that it's going to go up, rainfall. If it is orange or red, 2/3 of the models say it's going to go down. If there are points, black points, that means that 90% of the models agree in the sign. Now, first comment, see where the black points fall, where there's no people. And second comment, if one model says precipitation will increase by 5% and another model says precipitation will increase by 50%, they're both painted with blue. Now, at regional level, if you take one of those regions, which is the Horn of Africa, East Africa, where Kenya is, that's an area where the models coincide pretty well, right? 90% of the models agree that rainfall is going to go up. Now, if you look at the runs of individual models, this is a picture that you get. True, 90% of the models say that the rainfall will increase. There's some that say it will increase 20%, some say that will decrease 5%. And yes, there is an average. There is a thicker line here. Now, how much do you believe that line with that spread? This is state of the art. This is science today, 2014. Best science. And this is for big windows. The truth is that most often, most frequently, we're not interested in big windows or in the whole world. We're interested in a country, in a region within a country. Uncertainties at that level are much, much worse. They're huge. Now, what is the conclusion of this first set of slides? Climate change scenarios, future climate, they're uncertain. And in fact, if you talk to the IPCC scientists that were involved in developing these scenarios, they were not intended to be connected to economical models or crop models or beef production models. They were intended as an alert for the world, alert that says, we are getting into trouble, and if we don't change the way that we are developing, we will be in deeper trouble. But they were not intended to generate scenarios of corn production or beef production. In fact, when most of the scientists see how these models are being used, they go nuts. They get really worried. And in fact, you still see in the literature, in scientific literature, peer-reviewed journals, you see results like this, in which there are studies that show that, for example, by 2080 in Mexico, maize yields will be decreased by 20%. And if you go to the pixel level, it probably says 18.5%. Now, where is this coming from? It's coming from linking crop models with this huge uncertainty in the precipitation. Yes, you can have a result with a mean, but how valuable that mean is. And the bad thing is that this is a lot easier to understand by a policymaker, a decision maker, than if you start talking about uncertainties and ranges and possible scenarios. This is very easy to understand. And that's why it's so dangerous. You can make a lot of decisions believing this. And some of those decisions may turn to be pretty bad. Now, one of the things that some parts of the scientific community have been doing to improve the situation is saying, you know what, the problem with the climate models is that the resolution is just too coarse. So what we need is more detailed models. We need to go to higher resolution models. That's what's called the downscaling, improved resolution. Now, downscaling is very good for, say, seasonal forecasts, for what can happen the next 3 months. But the main driver of these downscale models is still the big models, the coarse models. And so all the uncertainties that are contained in the big models are transferred to the smaller models, to the high-resolution models. And in fact, sometimes you even add uncertainty. So this is not a solution. When you see maps, they look great. They have very nice detail. You see the Alps, you see the Andes, you see. The truth is that the uncertainty in those values, even when the maps are so pretty, is the same as when you use the coarse models. And so this is the situation where we are now. Again, I strongly believe that science is good when it helps to inform policy, inform actual decisions. And what is the situation today? Decision makers, including policy makers, they're pressured to act today. The problems that they are most commonly focused are short-term problems. A minister is usually more interested in this afternoon and next month and maybe up to 4 or 5 years than 80 years in the future. On the other hand, the scientific community has been providing policymakers with scenarios that are focused in 2100. And then when these policymakers start understanding more about these scenarios, they realize they're extremely uncertain. So that's a perfect recipe for paralysis. You provide information that is far in the future and that is very uncertain. So there's nothing I can do. And that's the situation today. If you look around, adaptation to climate change is not a priority in most development programs, in government programs. It is in every discourse. But when you start looking, okay, but what are they actually doing in adaptation? Mitigation, there's a lot of plans. More energy, renewable energy, less deforestation. Adaptation, very difficult to see. And so the conclusion of this is we need different approaches. One of the things we need to realize is that climate changes, varies at different temporal scales, just like prices. And to give an example, I'm going to use the Sahel, just south of the Sahara Desert in West Africa. And that graph is showing the annual precipitation for the Sahel in the last 110 years. Now, one question that you may ask is, in the Sahel, did we witness changes, climate changes in the long term? And you can adjust some model, and yes, there was a change at that scale, about 180 millimeters difference from the beginning of the 20th century to today. The other thing that you see is that there are some decades, some groups of years, where rainfall tended to be above average, and some years where rainfall tended to be below average, decades. So there is a second question, is there any variations at the decadal time scale? And yes, there is variation. And already the magnitude of that decadal variability is bigger than the long-term climate change. 250 millimeters from one decade to the next one. And then you have the rest. Once that you take, I'll remove the effect of this climate change in the long term. I'll remove the decadal variability. And I remain with what happens year after year. One year you have a drought, next year you have floods. The interannual variability, that's where most of the story of variation is. You see 290 millimeters from one year to another one, and you see 400 millimeters from 1 year to 3 or 4 years later on. This is what really affects societies, production systems, etc. And you may ask yourself, how relatively important are these different scales? So how much of the story I capture in each one of these temporal variability? And the numbers are this, in this case. Only 18% of the whole story, I see it in the climate change scale. In this case, where there is a important decadal variability, 27% of the total story is found at that temporal scale. And where is most of the variability? Year to year, interannual, 55% of total. And this happens all over the world. I'm not going to show numbers just to save some time, but all over the world, climate change explains 10 to 15% of what happened during the last century. In some places where you have decadal variability, that decadal variability explains 15 to 30%. The rest, the story, the majority of the story is in this year to year, 60 to 90% of the variability. So, and I'm going to skip these maps. So when you go to a place, a real case like Southeast South America, South Brazil, Uruguay, Argentina. This map is showing changes in precipitation in our summer months from early 20th century to late 20th century. It is showing that in some areas, for example, in areas of Uruguay or the Pampa province in Argentina, precipitation in the summer increased quite a lot, 50%. That's a lot of change. And in fact, those changes, for example, in this area, in western province of Buenos Aires and the province of La Pampa, that allowed farmers to grow crops in areas where they couldn't grow crops before. There's more rainfall now, they can sustain soybeans, wheat. Now, the question is this a change that will continue forever? Or is it a change that is part of this decadal variability? And they had a set of decades that were wet, and now we're getting into a set of decades that are dry. Understanding that is very important. You can imagine the consequences that that has. If we only look at the climate change, we will not even pay attention to that. The climate change, I mean these long-term, small changes. So what this is saying is we need to start looking at other temporal scales. So what are the initial thoughts of all of this? The scenarios that are based exclusively on climate models, they're uncertain, they're worse for precipitation, and they're much worse for local level. The scenarios that only focus in what we popularly call climate change, they tell us a minor part of the story of the past and probably will tell us a minor part of the future. We need to start looking at other scales. And the majority of the variability, of the variations in climate is found in this year-to-year variability. So, as we said before, we need a new approach. We need to start thinking differently about climate change. One of the things that we are doing in our institution is saying climate change is not a problem of the future. Climate change is happening already. It's a problem of the present. Second thing, some of the most damaging impacts of these changes in climate are expected in changes in the frequency of, for example, extreme events. More frequent droughts, more damaging droughts, more storms, more floods. And therefore, learning to cope with current climate variability, learning to cope with current droughts, current storms, current floods, will result in productive systems, production systems in societies that are less vulnerable to these variations in climate today, and therefore will likely be less vulnerable in the future to this increased variability. With the advantage that the actions to improve adaptation to current climate are needed today. So they are much more interesting for a policymaker than thinking of the year 2080. Now, there are some decisions that need information of the future, but we don't have to go to 2080. Let's focus in the next 10 to 30 years. And most importantly, let's not think of climate change as one separate scale of variation. Let's put this into the whole package of climate varying at different time scales and produce information that is relevant for the decision we're trying to make. I would dare to say that for most decisions, the most important scale is this year-to-year variability. For some infrastructure investments, we'll probably need to have 10 to 30 years. So, and here I'm going to use an example that a colleague of mine from this country uses and I like very much, is we need a new paradigm, just like in the previous presentation. What is the paradigm that we have been using until today? Is Noah's Ark. Why? Noah got perfect information about climate. It's going to be a cataclysm. Built infrastructure, saved biodiversity. But it's great. I mean, this is wonderful. I wish we could do this. But we will not have perfect information. I just show you. The best tools that we have are far from being perfect. So we need a new paradigm. And this colleague of mine calls the paradigm of the ginkgo biloba. I don't know if you know, ginkgo biloba is a tree. I don't know what is a common name. But apparently when the atomic bomb was dropped in Hiroshima, everything was killed in a radius of several kilometers, right? Somehow, 6 of these trees survived. It was the only thing that survived. They're still alive, and as you can imagine, these trees have a very big symbolic meaning in Japan. Now, the question is how? Why? Why did these trees survive? And one possibility is that related to how old this species is. It's a 2-million-year-old species. So very likely through the evolution of this species, these trees probably confronted very unfavorable extreme environments. So extreme that maybe they gave them the flexibility to adapt to something that never confronted before, like an atomic explosion. So, and this is a new paradigm. The truth is that we don't know what the climate will look like in the future. That's the truth. We have some ideas, but we don't know. And we need to learn to adapt with flexibility to a wide range of possible conditions. Considering a wide range of possible conditions, what are the strategies, the interventions that are more likely to succeed? Stop thinking that we know what will happen with climate, because we don't know. The last concept that I wanted to discuss with you is again related with this relevance of scientific information trying to inform decisions and planning. Clearly, the proportion of science, advances in science and technology that ends informing actual decisions in the private sector or policy in the public sector, the proportion of that is relatively low. We would like to see a lot more than that. And why is that? One of the reasons why that happens, we believe, is the way that we work. How do decision makers work? How do they approach a problem? They never approach in one dimension. Several things at the same time, several variables. I'm not going to get into details. You know what I'm talking about. It's never one dimension. It's never rainfall. It's rainfall prices, unions, votes. Now, how do we advance in the scientific community? Exactly in the opposite. We're getting better and better in smaller and smaller areas. And what we generate is what one colleague of mine calls islands of knowledge in a sea of ignorance. We know a lot about small things. We don't connect those small things very well. And decision makers navigate the sea of ignorance. They don't go hopping from island to island. So we need to start producing science in a way that is integrated. Knowledge is integrated to actually inform decisions. And there are several things that we can do to integrate knowledge and produce information that is not only interesting and publishable in peer-reviewed journals, it's also understandable and usable by the people that are making decisions. Some of the things we can do is promote the establishment of interdisciplinary groups, or be very careful that we are informing a network of knowledge that is already the source for the people we're trying to inform. Scientific community is almost never the direct source for a minister. There's a lot of links in between. The other thing is develop tools that can integrate this knowledge. In Uruguay and in other countries of the world, we are using this approach, and we call them information and decision support systems. There is a very nice example in Uruguay that I will be glad to discuss with you, in which what we are doing basically is developing these tools where we connect climate information, prices, data from remote sensing, monitoring, existing databases, simulation models under a geographic information system, and create maps, for example, that are very easy to understand. Traffic color maps. Green, no problem. Yellow, be careful. Red, no. Behind that, you can have a very sophisticated science, very sophisticated knowledge and disciplinary work, but you need integrated information like this. And with that, we're producing things like in that list. Studies for early warning systems or early response systems, producing insurance that are accessible for even small farmers, studies that assess the feasibility of new technologies, etc. So basically, tools that can allow you to study problems at different spatial resolution, from a whole country to a region in the country, all the way to a single farmer. Different temporal resolutions, longer term, decadal variability, weather scale. And they're easily understandable, and therefore they trigger action. Again, they're not just interesting, but understandable and actionable. So, final comments. Again, the key action when looking at climate change is mitigation. It's going to the source. And everything that I told you about how uncertain future climate scenarios, that is not an impediment to take action today. We have to take action. That's where we have to put a lot of our efforts, in reducing net emissions. Regarding adaptation, we need this new approach, an approach that is more like climate risk management, integrated climate risk management. And being aware that a lot can be done today to improve the adaptive capacity to future climate, a lot. When a Minister of Agriculture comes to our institution and says, please help us to improve adaptation to climate change, our immediate question back is, are you well adapted to current climate? When you have a drought, you have a system that works very well. If not, let's start by that. That's the best thing to improve adaptation to today and to tomorrow. If we need to work in future like we do, we don't have to go to 2100. We can work in shorter terms. And on science improving contributions to decision making, we need these integrative tools and integrative approaches. Interdisciplinary groups, interdisciplinary research, and tools that can actually result in knowledge that is integrated, that is understandable, and therefore that it triggers action. Thank you very much.
Thank you, Dr. Baethegen. We now have some minutes for questions.